So in this video we will discuss the last part of incompressible viscous flow in pipes. So we will discuss about the friction loss, and we will find out the friction factor for laminar flow and turbulent flow, and also we will find out the minor losses like the sudden expansion, sudden contraction, entry and exit losses. We have already discussed the steady flow energy analysis for a 90-degree elbow, and we have defined the kinetic energy correction factor to write the energy equation in this form to find out the head loss between two sections. So here alpha 1 and alpha 2 are the kinetic energy correction factors at section 1 and section 2. So the total energy at section 1 minus the total energy at section 2 between any 2 points will be equal to the head loss in terms of the unit of length. So this equation can be used to find out the head losses. So basically the major loss in case of a viscous pipe flow takes place due to friction. So that is why the friction loss is known as the major loss. So that first we will discuss, and we will find out the friction factor. So for a fully developed flow through a constant diameter pipe, so that expression we have discussed, the energy equation is for variable cross sectional areas. But if the cross sectional area remains same for a pipe and in the fully developed region, so alpha 1 v1 square by 2 equal to alpha 2 v2 square by 2. Here v bar is the average velocity at that cross section. So that means the kinetic energy considering the average velocity remains the same if it's a fully developed flow and diameter remains constant. So from the energy equation, so these two parts will cancel. So hence the head loss for unit mass will be P1 minus P2 by rho plus G into Z1 minus Z2. And for a horizontal pipe, Z1 equal to Z2. So head loss for unit mass equal to P1 minus P2 by rho. So that means it is delta P by rho. So that's why the pressure drop between the 2 points divided by the density will give you the head loss for unit mass. So this equation is valid for laminar flow as well as for turbulent flow. Now for laminar flow, already we know delta P equal to this much. We have derived this equation already. Considering a small element of fluid in case of a fully developed laminar flow, so we have found that delta P equal to 128 mu L Q by pi d fourth. Now here I can write down Q in terms of the average velocity. Q is the volumetric flow rate, so it is the product of average velocity and the area pi d square by 4. So this is equal to 32 L by D into mu B by D. Now I can write down this part in terms of the Reynolds number, because already we have defined Reynolds number equal to rho u d by mu. So what you have to do, you have to multiply by rho and v to the numerator as well as to the denominator. So automatically the term rho u d by mu will come into picture, and we can replace that quantity by Re. So this quantity can be written like this. So your HL, small HL, so small HL is the head loss per unit mass. So equal to 64 by Re into L by D into V average square by 2. So this you remember, we will use this later. So for laminar flow, okay, for theoretical analysis we have done and we have derived this, so we have simply used this. But for turbulent flow, already we know that it's completely unpredictable flow, so there is no analytical procedure available, and experimental results we can use, or we can do the dimensional analysis for the turbulent flow. So let's we will do the dimensional analysis. So in case of a fully developed flow, for a turbulent flow, sorry, the fully developed region, in the fully developed region for a turbulent flow, the pressure drop depends on the diameter of the pipe, the length of the pipe, this is the surface roughness of the pipe surface, this is the average velocity, density and viscosity. So the pressure drop depends on these 6 dimensional quantities. So using Buckingham's pi theorem, so in the non-dimensional analysis there is an important theorem known as Buckingham's pi theorem. So in Buckingham's pi theorem, by using Buckingham's pi theorem, we can get non-dimensional numbers out of these dimensional quantities. So there are how many dimensional quantities? 6, and this is 1. 7 dimensional quantities. So these 7 dimensional quantities can be, the unit of these 7 dimensional quantities can be represented by using 3 units: M, L and T. Mass, unit of mass, unit of length and unit of time. So there are 7 dimensional quantities can be written using 3 units. So according to Buckingham's pi theorem, we will get 7 minus 3, that means 4 non-dimensional quantities out of these 7 dimensional quantities. So delta P can be non-dimensionalized by using, by dividing this by rho into V square. Delta P by rho V square becomes a non-dimensional. So this is one dimensional quantity. Then the Reynolds number also we will get by using these quantities. So mu by rho Vd, this becomes again a non-dimensional number, 1 by Re. L by D, this is also becomes a non-dimensional number, and epsilon by D, this is also a non-dimensional number. So out of these 7 dimensional quantities, we got 4 non-dimensional numbers. So del P by rho V square is a function of mu by rho Vd and L by D and epsilon by D. So del P by rho V square is a function of Reynolds number, L by D and epsilon by D. So del P by rho V square already we know. We can express that in terms of HL by V square, which is a function of Reynolds number, L by D ratio and epsilon by D ratio. And experiments show that HL is proportional to L by D. So you can take L by D out of the function. So HL by V square equal to L by D and a function of Re and epsilon by D only. So we will divide this V square by 2, because half V square means it is related to the kinetic energy per unit mass. So it is better to express in terms of HL by half V square is equal to L by D and a function Re and epsilon by D. So this we got from the dimensional analysis. Now this quantity, the function is defined as the friction factor. So the friction factor is defined as a function of Re and epsilon D. So your HL equal to, we can write down, just replace this by F. So your HL becomes FLV square by 2D. So this is the head loss per unit mass. Now you can divide by G both sides, it becomes a head loss in terms of unit of length. So HL equal to FLV square by 2GD. So this is famously known as Darcy-Weisbach formula or simply Darcy equation to find out the head loss due to friction, provided you know the friction factor. So if you know the friction factor, which is a function of Reynolds number and epsilon by d, then we can find out the head loss due to friction in case of a viscous pipe flow. Now, F is determined experimentally for turbulent flow, and a lot of experiments has been done by L.F. Moody, and he put all the results in a diagram which is known as Moody's diagram, and from the Moody's diagram we can find out the friction factor for laminar flow as well as for turbulent flow at a different epsilon by d ratio, because friction factor is a function of Reynolds number as well as epsilon by d. If Reynolds number is less than 2100, it is laminar flow, and if Reynolds number is more than 4000, it is turbulent flow. So at any RE value and for any epsilon by d value, you can get the friction factor from the Moody's diagram, which we will discuss in the next slide. Now for laminar flow, already we know HL equal to 64 by RE into L by D into V square by 2. Also HL is expressed as F into L by D into V square by 2. So F equal to 64 by RE. So from the theoretical analysis we got this. So if you know the value of RE, then friction factor is 64 by RE. This formula we can use even without using Moody's diagram. For laminar flow we can use this simple formula, but for turbulent flow, to get the value of the friction factor, either we have to use Moody's diagram or there are many empirical correlations like the Viscous correlation. For this is valid for RE less than or equal to 10 to the power 5 for smooth pipes basically. So there is no effect of surface roughness epsilon. For smooth pipes we can use this F equal to 0.316 divided by RE to the power 0.25. But if you will take the effect of the surface roughness, then this Colebrook correlation can be used. So F, but it is implicit function. So on both sides, left side as well as right side, the F value is there. So it is a implicit function. But still we can solve this if you know the RE value and if you know the epsilon value. So this gives the friction factor for rough pipes basically. But it is better to use the Moody's diagram instead of remembering these formulas. So for any RE value we can get the friction factor for turbulent flow using the Moody's diagram, and also for turbulent flow the wall shear stress is this much. This also you have to remember. So all these equations for turbulent flow are developed using the experimental data. So they are known as the semi-empirical correlations. So these are the roughness values for different material of the pipe. So I have taken this from Introduction to Fluid Mechanics book by Fox and MacDonald. This is very good book for fluid mechanics. So the roughness values are given in mm as well as in feet. So this is the Moody's chart. You see in y-axis the F value you have to find out, provided you know the Reynolds number, you know epsilon by 2. So this is a straight line because for laminar flow the friction factor is 64 by RE, so it is inversely proportional to RE value and it's a straight line. So from this line we can get the friction factor for any value of the surface roughness, and this dotted line is for fully turbulent flow. If you know the RE value and epsilon d, then you can find out the F value for the turbulent flow. So for uh, smooth pipes as well as for the rough pipes with different epsilon by d ratio and different Reynolds number, we can easily find out the friction factor for laminar flow as well as for turbulent flow. So this region is turbulent. So this is widely used throughout the world to find out the friction factors. So sometimes we also express the the factor as Fanning's friction factor. This F is known as the Darcy friction factor. So in the Darcy-Weisbach formula to find out the head loss, so it is known as Darcy friction factor, and also there is another friction factor known as Fanning's friction factor (CF). Also it is known as the skin friction coefficient, and the relation between them is this. So friction factor is 4 times Fanning's friction factor. So Darcy friction factor, or simply it is friction factor. But if it will be given as Fanning's friction factor, then you have to multiply by 4 to this to get the friction factor, so that you can use it in the Darcy-Weisbach formula to find out the head loss due to friction. And if you know the F or CF, then you can find out the shear stress at the wall equal to half into CF into rho U average square. So for laminar flow, turbulent flow, if you know the friction factor, you can find out the CF, then you can find out the shear stress at the wall using this formula. So now we can plot the total energy line along a pipe in the direction of the flow, as well as the hydraulic gradient line along the length of the pipe. So total energy line means it is the sum of all energies. So total energy is summation of pressure energy plus kinetic head as well as static head. All are in terms of the unit of length. So we can find out the summation of all these energies at different locations, and if we plot this along the length of the pipe, we will get the total energy line. But hydraulic gradient line is the display of the only pressure head and static head. So this part is neglected, the kinetic part is neglected. So find out the pressure head and static head at different locations of the pipe and plot it. So basically it is the piezometric head. So the summation of the pressure head and the static head is known as the piezometric head. So the variation of the piezometric head along the length of the pipe is known as hydraulic gradient line. So due to viscous effects, the energy is lost along the direction of the flow inside a viscous pipe. So the total energy line will decrease in case of a viscous flow in a pipe. So in this way we can find out the major loss by friction. So most of the losses happens due to friction, so that is why it is known as major loss. So along with these friction loss, there are also some minor losses due to change of the geometrical shape of the pipe. So sometimes the pipe becomes suddenly expanded, sometimes a large pipe diameter becomes suddenly contracted, as well as there is entry to the pipe, there is exit to the pipe. Sometimes it is requirement for a 90-degree bend, sometimes there is a requirement for 180 bend, U bend. So due to these geometrical changes, also there are some losses take place, but these losses are very less compared to the friction loss. So that is why these are the known as the minor losses. So we will discuss the first loss. Minor loss is due to sudden expansion. So sudden expansion means initially for some portion the pipe length diameter is less, then again suddenly it becomes expanded to a large diameter. So due to this expansion, the streamlines, you see how they change their path. So the streamlines modify the path like this towards the top wall and the bottom wall. So towards the corner of the expansion, some fluid are trapped, and that fluid cannot flow with the main flow, and they are recirculating. So they are known as the turbulent eddies. They are trapped in the corner. So that trapped portion also will impart some force in the main direction. So we can write down the momentum equation between section 1 and 2. So momentum equation means it is the rate of change of momentum is the sum of all forces along the direction of the flow. And from the experiments it is found that the pressure of the eddies trapped in the corner due to sudden expansion is equal to pressure at the upstream position. So this pressure and this pressure nearly equal. So P dash is the mean pressure of eddies, and P1 is the pressure at the upstream position, that means a low diameter portion of the pipe. So P dash equal to P1. If you will use this in the momentum equation, so momentum equation means, so what are the forces along the direction of the flow? It is P1 into A1 plus P dash into A2 minus A1 means, so this portion is difference of the area A2 minus A1. So that's why A2 minus A1 is used. So minus P2 A2, at 2 pressure will be towards left, so it is minus is equal to rate of change of momentum. So mass flow rate rho into Q into change of velocity is the rate of change of momentum. So P2 minus P1 into A2 equal to rho into Q into E1 minus U2. So this one equation we got from the momentum equation. Now continuity, volumetric flow rate equal to A2 into U2. So put this value of Q here so that the whole expression will be in terms of the pressure and velocity only. So P2 minus P1 equal to rho into U2 into U1 minus U2. Now we will use the Bernoulli's equation between section 1 and section 2. But Bernoulli's equation in the original Bernoulli's equation with assumption of inviscid flow, incompressible flow, steady flow, the total head remains same. So at section 1, sum of all heads will be equal to the sum of all heads at section 2 if the assumption is inviscid flow. But this is the case of a viscous flow, so there will be some losses. So total energy at section 1 will not be equal to the total energy at section 2. There will be some losses. So we can write down the pressure energy plus the kinetic energy at section 1 will be equal to pressure energy plus kinetic energy at section 2 plus losses due to viscous effect. So from this equation we will get P2 minus P1 by rho equal to U1 square minus U2 square by 2 minus G into HL. So you replace P2 minus P1 from this equation, put the value of this here, then do some little rearrangement of the equations, so we will get HL. So the loss of head due to sudden expansions, I am using L for all the losses. You can replace L by E means expansion, L by C contraction, okay, but all are the losses. Even F also I can write down for friction, okay. So head loss in terms of unit of length equal to U1 minus U2 square by 2G. Now U1 A1 equal to U2 A2 from the continuity, so I can take U1 common, so U2 minus E1 I can write down in terms of the area ratio. So if you know the area A1 and A2 and velocity at 1, we can find out the head loss due to sudden expansion. Now next minor loss case is the sudden contraction. So sudden contraction means initially for some portion the pipe is having high diameter and suddenly the pipe diameter becomes less, so it becomes a sudden, so this area becomes a sudden contraction. So if you will follow two streamlines, extreme streamlines, the top one and the bottom one, so you see the sudden contraction is not the smallest area available for the flow. So after some distance from the sudden contraction, you see these are the streamlines. So this area is the minimum area available for flow. Also, you know, okay, the streamlines, the stream function study, the volumetric flow rate, we can find out between two streamlines as the difference of the two stream functions corresponding to those streamlines. So these are the two extreme streamlines. So the flow takes place between them. So the flow will be along this area. So the smallest area available for the flow between the two streamlines is known as the vena contracta, C. And the loss of head takes place due to the flow from C to 2. So from C to 2, it is similarly the sudden expansion case. So at C, vena contracta, the cross sectional area is minimum. At 2, it is more than the area at C. So it is similar to the sudden expansion case. So this we have to keep in mind. So at inlet, suppose P1, U1, A1 are the variables, and at vena contracta, the minimum cross sectional area, and at the exit 2, P2, U2, A2 are the values. So we can use the continuity equation between the vena contracta and the outlet or exit. So AC UC equal to A2 U2. So UC by U2 equal to A2 by AC. So here in the vena contracta, we can use a coefficient of contraction, which is the ratio of area at C divided by area at 2. So AC by A2 is the CC, coefficient of contraction. So the velocity ratio we can express in terms of coefficient of contraction. Now head loss from section C to 2, it is similar to sudden expansion. So already we have derived the formula for sudden expansion. So I can use this formula. So HL equal to UC minus U2 square by 2G. Now UC by U2 already we know. So take common U2 square by 2G, so that we will get UC by U2 minus 1. So this U2 by UC by U2 I can get in terms of CC, put the values. So the head loss due to sudden contraction is U square by 2G into 1 by CC minus 1 whole square. So this 1 by CC minus 1 whole square is a coefficient K we can get if you know the values of coefficient of contraction. This will be given in the problem. So from here you can find out K. So K value generally lies in between 0.5 to 0.7. So if you know K value, you can find out the head loss due to sudden contraction, which is K times U2 square by 2G. Now next is entry loss. So entry loss means it is sudden contraction, like flow from a large reservoir to a pipe. So generally the flow takes place from a large reservoir to a pipe. So it is similar to a sudden contraction, but area 1 is infinite. So if you put area 1 is infinite in the sudden contraction formula and K equal to half, you will get the head loss due to entry. So this is the head loss, half into U2 square by 2G. Similarly, exit loss means the discharge into a large reservoir, suppose at point 2. So it is similar to a sudden expansion, but area 2 is infinite. So in the formula for sudden expansion, put A2 equal to infinite. So you will get the head loss U1 square by 2G. Similarly, in a pipe, there may be the requirement for bends maybe 90-degree bends, or maybe for uh, U bends 180 bends. So that also similar to uh, the exit loss, but multiply by a constant, and this constant value depends on which type of band we use. So head loss due to band HL equal to K into U square by 2G. So in this way we can find out the major loss due to friction, also the minor losses due to all these 5 phenomena. So in case of a long pipe, all these things may happen. So we have to find one by one all the losses and sum of. Then if H1 is the head available at the inlet and H2 is the head available at the outlet, then we can write down H1 equal to H2 plus sum of all losses. So in this way we can solve the problems in a viscous pipe flow to find out the losses. So thanks all of you for watching the video. If you like it, please subscribe to my channel. Thank you.